Worksheet 3A, stress strain curve, about the material property, mechanical properties of material. And we have a stress strain curve in front with the stress in KSI and strain. This is normal stress and normal strain, by the way. Unit inch over inch, 10 power negative 3. So from that, there are two parts of the question. The first is using the stress strain curve, and they ask us to determine the proportional limit of the stress. So proportional limit is the limit in the linear portion of the stress strain curve. So basically from that we can have that point in the proportional limit point here from 0 to that, and whatever the stress that you receive here, that will be the proportional limit. So from that we can have proportional limit PL for that problem about it's approximate because the curve here. So 40 unit is KSI, 40 KSI. The U stress, and in this case, as you can see, the horizontal portion of the curve is not really easy to recognize, so that difficult to see where is the starting point that the material is yielding. So from that we have to use 0.2% offset method. 0.2% offset method. So from 0.2% is mean, what does that mean here? Go back to the 0.2%, the 0.2% here, that is epsilon equal to 0.2%, and that is 0.002, or it also equal to 10 power 3, and that exactly the point that we are looking at, that here, because the unit for the strain in here is inch over inch, 10 powers negative 3, and in this case the unit is inch over inch. And we just put the straight line parallel to the linear portion, straight line parallel to the linear portion. Let's make it straight now. Straight. Let's put the red to easy to see portion. And whatever it meet there, it will be find out the U stress. And from that, as you can see, it about 40 and 50, close to 50. Let's make approximate it. For that, the U stress here equal to, as you can see there, about 48 KSI. So it's very approximate in nature, but it use the number that makes sense based on the graph. And the next question is, what is the ultimate strength? Ultimate strength, so that is the maximum stress that material can pick. So here let's put that blue one, that is the maximum there, maximum it can pick. So somewhere there, so it's almost 50 and a little bit above the yielding stress. So from that we can see put about 49 KSI. So from that, the blue one, sigma ultimate equal to 49 KSI. Rupture stress or breaking stress. So rupture stress or breaking stress, let's put that in the blue one there. That is in the book they call it breaking strength, and this is also the rupture stress. All right, rupture stress in here. It can be also the same as the break-in strength in your book. So the same thing, break-in strength. So from that, as you can see in that rupture stress, if we get that blue and look at what happened in there, go to the vertical, and that we have it the rupture stress. So it's about 32, 33. So let's make that is the let make that sigma rupture stress. So it will be sigma b equal to, or break-in strength, like I say, about 32 KSI. So it is all approximate based on the graph. And if you want to see what is the rupture strength of this material, rupture strain, so it epsilon r, so it will be somewhere going down here. So you can see 20, 40, so about 42, and the unit in this case, as you can see, times 10 power negative 3, and the unit is inch over inch. But keep in mind, the question asks is rupture stress, so it's sigma b, not epsilon r. If they ask, you can do that. Modulus of elasticity. So in the elastic region, the ratio between the vertical and horizontal, so between the stress and strain, so as you can see, E basically equal to sigma over the associated corresponding strain. So yes, you can get any point. For example, at 2, 10 power 3 there, go up. The corresponding stress, as strain is 0.2%, is about 20 KSI. Or you can do the same, about 4, then it's 40, right? 4, 10 power negative 3, it could be 40 KSI. So from that, the corresponding number, so let me make it down here, go up there, and then we have there. So from that, we can plug in with that blue one. So you have 20 KSI divided by 2 negative 3 power 10 power negative 3, and from that you can get E about 10,000 KSI. This is inch over inch. If you go, so that unit is 10,000 KSI. So that part number 1 done. Now the part number 2, during a tension test on a half-inch diameter specimen, and the length of the gauge of this specimen is 2 inches. So basically that is L0, and this is the original diameter, D0. You record the force 3,000 pounds. The actual deformation, so that is delta in the length, right? In the longitudinal axis. The deformation in the longitudinal axis. And the diameter now is that. So that is the diameter after the test. So df, final diameter. What is the Poisson ratio for this material? So the question is, what is new? What is new? And as you can see, before we know what is new, we need to know what is the equation for new and find out each of the components in that equation. So if you remember, the new is equal to negative epsilon lateral divided by the epsilon longitudinal direction. So normal strain in lateral, in this case the diameter of the specimen, and the longitudinal is along the length of specimen. So from that, find out each of them. So let's find out the epsilon longitudinal. It will be equal to the delta longitudinal divided by the L naught, the length in the longitudinal dimension, and that all are given. So we can have epsilon longitudinal equal to given there 30.5 times 10⁻⁴ inches over the length, original length 2 inches, L naught, so 2 inches. This is inch, this is inch. From that we can have epsilon longitudinal equal to 1.525 10⁻⁻3, and the unit inch over inch. So that is the normal strain in the longitudinal axis or along the length of the specimen. And then go ahead to find out the epsilon for the lateral. So epsilon for the lateral. So basically that is the diameter. So as you can see that is the delta of the diameter deformation along the lateral, in this case the diameter of the specimen, original diameter. As you can see that is d naught, and then if it elongate, then the diameter it will be contraction here, and that become a d final, and the change between those two, the delta d for the diameter, it basically it equal to the final minus d0. When we know the deformation delta along the diameter, delta d, then we can go back to the normal strain in lateral direction, epsilon lateral equal to delta d over the original diameter, d naught. And both information we have, so we can go ahead to get the epsilon normal strain in lateral, delta d, final diameter minus original diameter. So you have 0.4998 inch original diameter specimen, 1/2 inch, so 0.5, and the unit is inch, divided by original diameter is 0.5 inch. From that we will have epsilon lateral equal to -4, negative stand for in this case, as you can see, because the specimen is elongate in the longitudinal axis, then the lateral have to be contract. That's why it's negative. The diameter is reducing. Times 10 power 4 unit inch over inch. So from that we have both epsilon lateral and epsilon longitudinal. So we can go ahead to find out new Poisson ratio is equal to negative epsilon lateral divided by epsilon longitudinal components for the normal strain. So from that we can plug in lateral negative 4 10 negative 4 inch over inch divided by normal strain in longitudinal axis. So it's 1.525 10 negative 3 inch power inch. So from that we get new the Poisson ratio equal to 0.26, which it makes sense because normally it go in the range between 1/2 and 3/4. So with that we finish this problem 3A for lesson 3.